Thank you for joining me in this presentation about the role of hydrogen in the chemical site. My name is René Slaghek and I'm a chemical engineer by profession, and I have 35 years of experience in the chemical industry, mainly in urea and melamine. I'm currently employed by Cytec Services and work as head of technology within Brightsite on transition paths and system integration specifically for Chemelot. In that respect, I'm also the project manager of the Chemelot sustainability team, a team comprising of all sustainability officers of the Chemelot site. As you all know, the driving force behind the fight against climate change arises from the Paris Agreement of 2015, where a maximum temperature rise of 1.5 to 2 degrees centigrade was set as the goal to be reached by reducing greenhouse gas emissions. And in dealing with the challenges we are facing in fighting the climate change, hydrogen keeps popping up as a very important substance that can and will solve a lot of our problems. In this presentation, I would like to show what role hydrogen can play in an integrated chemical site such as Chemelot, where concrete issues are addressed, possibilities explored, and options defined and evaluated, aiming to reach a true sustainable future. An integrated chemical site like Chemelot produces a variety of basic materials that are applied in many consumer products that enhance today's welfare and drive sustainability in various ways, such as insulation and lightweight materials. Now, they are, at this point in time, irreplaceable at the enormous scale that they are being used. And some of these basic materials like fertilizers, melamine, caprolactam, and acrylonitrile use ammonia as a basic building block. And this ammonia is now produced out of natural gas. Other basic materials like polyethylene, polypropylene, elastomers, and acrylonitrile are produced from ethylene and propylene. And these building blocks are produced by naphtha cracking. And the production of these basic materials, of these basic building blocks, ammonia, ethylene, and propylene, that emits in large amounts of greenhouse gases to the environment. If we look at the site like Chemelot, it uses roughly 1.5 billion cubic meters of natural gas, 4 megatons of naphtha, and it requires 220 megawatts of electricity. And some 65% of those greenhouse gas emissions originate from the production of the basic building blocks. Now, the question, of course, is how can such an integrated site become climate neutral? Well, the answer is fairly simple. You just have to eliminate all the greenhouse gas emissions. The reality, of course, is that it's not so simple. And for the answer, you have to look in more detail at all the sources of the greenhouse gas emissions. If you look at the CO2, that's coming from the use of fossil resources for the production of ammonia, ethylene, propylene, but also utilities like steam and electricity. And they need to be eliminated. At least the emissions need to be eliminated. There are also other greenhouse gas emissions like laughing gas and methane that also need to be eliminated. But for this presentation, I will focus only on the first part and not on the CO2 emission reduction and not on the other greenhouse gas emissions. If we start at the bottom of the list, the electricity, then it's pretty simple. We can just stop producing electricity on site and the CO2 emission will then, of course, be terminated. This will require the electricity to be sourced from outside. And of course, this needs to be green electricity. It's a relatively simple and easy way to implement a CO2 emission reduction, but a little small detail, that the green electricity that will be needed in the amounts that we need in the future, and even today, are not currently available. Next, if we look at the steam production, by executing energy savings projects, the dedicated production of steam via natural gas can be reduced. And for balancing the steam supply and demand on site, electrical boilers can be applied. And the realization of this CO2 emission reduction requires multiple technically complicated and high investment projects, but it is surely doable. Which brings us now to the two remaining items, ammonia and ethylene propylene production, the production of the basic building blocks. Let's start with looking in more detail to the production of ammonia. Ammonia production basically consists of a steam reforming step where natural gas, steam and air are transformed into a mixture of hydrogen, carbon monoxide and carbon dioxide. After the downstream processing step, a gas consisting of hydrogen and nitrogen remains, which is reacted to ammonia in the well-known Haber-Bosch process. Now, as you can see, carbon dioxide is emitted in two places in this process, in a pure form coming out of the downstream processing and in the diluted form in the flue gases out of the SMR. The pure carbon dioxide can be captured and stored in, for instance, empty gas fields. This is commonly known as CCS. In this way, 2/3 of the carbon dioxide emissions of ammonia production can be addressed. Applying, however, the same solution for the flue gases is a costly option. Moreover, the CCS solution is seen by many as a temporary solution, since it doesn't eliminate the use of fossil resources, nor does it avoid the formation of carbon dioxide. So in the desired sustainable future, other solutions need to be found. Switching to non-fossil hydrogen can eliminate not only the carbon dioxide emission, but also the use of virgin fossil resources. Once you do that, only the Haber-Bosch part of the process remains, and no CO2 emissions. Next question, of course, is then, what options are there for sourcing non-fossil hydrogen? Well, one option is the FUREC project, which was recently announced by RWE, where municipal waste is used in the gasification process to produce hydrogen. This requires also an air separation unit to be added to deliver the required pure nitrogen for the Haber-Bosch process. RWE has announced to build a 40 kilotons hydrogen unit at Chemelot, processing roughly all the municipal waste of the province of Limburg. The current hydrogen demand at Chemelot is, however, 5-fold this amount. So other options are also needed. One other option is to produce hydrogen out of biomass gasification, like the Bright2 initiative that is currently being researched at the Chemelot campus. Hydrogen can also be produced via electrolysis. This demands vast amounts of carbon dioxide-free electricity. And as we've seen before, that electricity is not yet available. It is also possible to import green hydrogen. The amounts that we need at Chemelot requires pipelines, and these pipelines do not exist at this point today. Although there are a number of projects underway to lay pipelines to Chemelot, but at this point in time they are not there. It is highly probable that in the future a mix of hydrogen producing technologies will emerge to make the complete transformation of the production of ammonia without emitting carbon dioxide and the use of fossil resources. So in this way we can produce ammonia without emitting any CO2 anymore. Now let's take a look at the production of ethylene and propylene. In the steam crackers, naphtha is cracked with steam into smaller molecules. The form methane is used to heat the furnaces. And the CO2 is emitted from these furnaces. The products of the cracker will ultimately lead to other, even larger carbon dioxide emissions elsewhere, for example, due to the burning of plastic waste. And so to become climate neutral, an important step is to replace the fossil naphtha. And this can be achieved by processing plastic waste into pyrolysis oil that can be used as a feedstock for the cracker. The pyrolysis oil needs treatment with hydrogen to make it suitable for processing in the steam cracker. The recently announced project of Plastic Energy and Slaghek is underway at Chemelot to produce some 20 kilotons of pyrolysis oil from plastic waste. This option does not, however, reduce the carbon dioxide emissions of the cracker. But somewhere else, carbon dioxide reduction is definitely taking place since the fossil naphtha consumption is reduced. So this is truly a circular solution needed for the sustainable future. But again, it doesn't reduce the carbon dioxide emission on site. And also, please bear in mind, the first project is 20 kilotons, where we need 4 megatons. By switching to bio-oil, at least a part of the emission will become biogenic of nature. The required amounts of bio-oil, like I said, 4 megatons of naphtha at Chemelot alone, are however not now nor in the foreseeable future available. So how can we eliminate the CO2 emission then? Well, one option is electric cracking. This requires, again, enormous amounts of CO2-free electricity. But by heating the furnaces with electricity, the carbon dioxide emission is eliminated. Another option is the Milena cracking process of Sinova. This process, in this case using waste plastic, contrary to the biomass that the wood that was mentioned in the previous presentation, this process produces a similar product package as coming from out of the furnace of a cracker. It is of course also possible to heat the furnaces with hydrogen. But if this hydrogen is produced from wind or solar electricity, it's much more desirable to use the electricity directly out of efficiency point of view. Now, electric or Milena cracking eliminates the carbon dioxide emissions of the crackers. But a new challenge arises: what to do with the methane that is still being formed. Burning the methane to generate heat will automatically lead to the same carbon dioxide emission that was just prevented by the electric or Milena cracking. So we have to look for other options. Well, the methane can of course be used as a feedstock for the ammonia production. But since only a smaller part of the carbon dioxide in this case is biogenic of nature, a combination with CCS is still required. Another option is to use the methane to produce hydrogen in an autothermal reformer, but also then a combination with CCS needs to be made. Both are excellent temporary solutions, but as said before, CCS is not deemed to be the final solution. A more interesting option is the use of plasma technology to generate hydrogen out of the methane without emitting carbon dioxide. The carbon can be harvested as carbon black, but even more interesting is the option where the carbon is transformed into acetylene or preferably ethylene. In this way, the carbon efficiency of the raw material of the cracker is strongly increased, and on top of that, the generated hydrogen can, for example, be used in the production of ammonia and the hydrogenation of the pyrolysis oil. Now, commercial plasma technologies based on processes towards carbon or acetylene already exist for many years, and at Brightsite we are investigating the process towards ethylene, and some presentations on that will be presented shortly. Transforming basic building blocks like ammonia and ethylene into sustainable substances makes it possible to transform the complete portfolio of products of virtually all site uses into sustainable basic materials. There is, however, not one technology for producing the sustainable basic building blocks. As multiple technologies present themselves, each with their own pros and cons, a variety of technologies will emerge, and hydrogen will play an important role in many of them. This all indicates a drastic change of our current conventional chemical industry. In our future circular society, a new upstream industry will take shape. And this future grain chemical industry will not only need many different technologies, but will also use a wide variety of resources ranging from waste, biomass, green hydrogen, to vast amounts of carbon dioxide-free electricity. In this way, today's fossil feedstocks that produce our basic building blocks can be replaced and carbon dioxide emissions reduced. So looking back at the first slide, the chemical side as it is today will change. New disruptive technologies such as gasification and pyrolysis processes but also myelina cracking and plasma technologies will take an important role. An integrated site like Chemelot offers many opportunities for these developing technologies, as the variety of existing and new processes makes new synergies and energy optimizations possible that are difficult to achieve in a standalone position, and will accommodate the transformation into a sustainable chemical site with a sustainable product portfolio. Of course, these are simplified diagrams of the processes at a site like Chemelot, but they do give an inclination of where we are heading, in my opinion. A lot more can be said and shown on this topic, but for now I would like to thank you for your attention, and if you have any questions, I'm open to answering them. Thank you.